Good morning. I'll be talking about efficient computation of MHP analysis. Let us start by understanding what may happen in parallel analysis or MHP analysis in short. Let us consider a program represented as a graph. The rectangles here show simple statements and the dashed edges like these two, they represent control edges. These control edges can be seen as if then else or if or while, etc. Right? And we also have solid edges that are representing task creation and join edges. For example, S112 creates two tasks, S1121 and 1122. And at S15, three tasks join. So that's a join. That's a join node. Okay. In MHP analysis, we may ask a question like, may S121 and S122 run in parallel? This is easy to answer. Yes, they do. Here is one more question. What all statements may run in parallel with S1111? And this is a bit more trickier than the previous one because of the presence of this node inside some complex control structures, inside a loop and so on. It so turns out this S1111 may run in parallel with a host of nodes, some inside the loop, some outside the loop. Okay? You may ask, why would you need such an analysis? It's a fundamental analysis and basis for many other tools and analysis. For example, for deadlock analysis, you need to understand which parts are running in parallel for whom you are constructing the deadlock analysis. Similarly, data race detection. Prior work has been done that shows the use of MHP analysis for slicing, dependence analysis, optimizing, even in IDEs to mark statements that may have data races and deadlocks. Okay? Hence, the speed of MHP analysis plays a key role in the speed and effectiveness of these tools. Okay? So we want it to be as fast as possible. There are two typical key questions asked in the context of MHP analysis. For a given statement S1 in a program, compute which all statements may run in parallel with S1, MHP S1. There is another type of question that is asked. Given two statements S1 and S2, may they run in parallel and under what condition? MHP S1, S2. Corresponding to these two key questions, we will also see two auxiliary questions that are commonly asked. For all statements S1, compute MHP S1, or for all pairs of statements, compute MHP S1, S2. Right? By the way, my apologies for the background noise. Today the cuckoos and the crows seem to be quite active and I don't seem to have any control on them, as if I should. Anyways, okay, we are talking about may happen in parallel analysis. We are talking about MHP analysis. Pay for attention to the may part here. This is conservative may analysis for languages that support async, finish and atomic parallelism, which is common in languages like Xten, XJ and so on. What do these constructs do? Async S creates a lightweight task. Finish S acts as a join or a terminating construct. And atomic S realizes global mutual exclusion. Okay? We will also talk about something called an escaping async. We will see that using an example. Look at this example here. I have a finish that starts that's kind of part of a task. Let's call that task as the parent task. In that I'm executing statement S1, and after executing S1 there is an async. So S2 and S3 may run in parallel, and the finish waits for all the tasks that are created in this, and after that S1 will start. Okay, and in this finish, this async is an escaping async. That is, if this finish wasn't there, this async would have run in parallel with more number of statements. So think of it like that. Okay, so we call this an escaping async. Okay, what's the state of the art? The best known solution to compute MHP analysis for all the four questions and challenges we talked about is given in a paper. Is given in a 2016 paper, where the key question 1 is answered at a cost of C cross N, where N is the program size and C is the number of concurrency related constraints. Auxiliary challenge 1 is also computed using the same complexity. Key question 2 using a complexity O of H, where H is the height of the program representation tree, represented in a tree, which is called as a program structure tree. Okay, PST is a program representation that we'll briefly look at soon. And the auxiliary challenge 2 is computed at a cost of OHN square. We will look at how we can extend these ideas in the case of IDEs, or IDEs as in integrated development environments, where the program keeps changing. As a user, you keep editing the program, and it's the goal of the IDE to maintain a lot of internal data structures, including MHP information. Say it wants to keep reporting about deadlocks or races and so on. Okay. Of course, the naive approach is to invoke this fast iMHP analysis after every change, but that can be expensive, and we don't want to do that. Okay, our goal is to present solutions that update this MHP information on the fly much faster. We will see. Okay, before we present our own solution, we will give a brief overview of what iMHP does. Okay, what it does, it starts by considering a code piece where all the concurrency related nodes are taken out. You gave it as an input the full program with some concurrency constructs and so on, like some finishes, asyncs and so on. It first takes them out, and then it says, okay, now that I have taken out all the concurrency constructs, let me ask myself this question: what is the MHP information? This is trivial. No statement runs in parallel with no other statement because there are no concurrency statements. Now we will add just the finished nodes. Still no parallelism. So again, the MHP information is trivially computed. Now let us add the async nodes. Now I have these async nodes which are added one by one, and I'm computing this MHP information just by adding these async nodes. Okay, and this is slightly tricky, but what the paper does is that it maintains sufficient information so that this information can be incrementally computed. The MHP information can be incrementally computed after addition of each async nodes. Okay, so first the finished nodes are added, then the async nodes are added, and the MHP information is computed. Then the atomic nodes are added. Atomic nodes enforce mutual exclusion between certain set of async nodes. And now we compute the MHP information after addition of each atomic nodes. And this is pretty cool in the sense, by computing this MHP information incrementally, by adding these nodes in a certain order, we are able to compute the MHP information for every element in the procedure. Remember, iMHP solution is also a intra-procedural solution. Okay? However, this solution is still not sufficient. Even though it's much faster compared to the prior work, it's still not sufficient in the context of IDE type of scenarios, where IDE stands for integrated development environments like Eclipse and so on. Let us see why is that so. Let's look at a simple program. I have finished statement. Inside that I have a statement async, which is S1, and async has a body S2. And after this async will run in parallel with the finish statement S4. S4 is again another async. If you look at the program, I can also represent it as a program structure tree where I have the finish has two children, S1 and S3. S1 is an async and S3 is another finish. S1, the body of S1 is S2. So S2 runs in parallel with the right hand side. Okay. So such a representation is called program structure tree, which is a concise AST, abstract syntax tree, if you want to think about that. Okay. What is the MHP information here? S0 runs in parallel with none, nor does S1. S2 runs in parallel with S3, S4, S5, rather S2 may run in parallel with S3, S4, S5, and S3 may run in parallel with S2 and so on. Okay? Okay. Let us make some small change in the code. Say added S6. Okay, so in the PST I have added S6. How does my MHP information change? No change for S0, no change for S1, no change for S3, no change for S4. For S2, I have added S6. For S5, I have added S6 and new information for S6. That's the moral of the story. Full recomputation for each change in the source is not only expensive but also avoidable. A single change does not always drastically modify all the MHP relations. Incremental update of MHP information for statements that depend on the modified statement is what you need to perform. Okay? And the exact changes to the MHP information will of course depend on the type of the statement that is added or removed. Okay? Here are our contributions. We present new algorithms to incrementally compute MHP information on the fly after each change. Okay? Just to give you a brief idea, the key question we can answer in order A times n, where A is the number of async nodes in the current immediately enclosing finish of the statement that is being inserted or removed. Okay? And compared to the state of the art, which is O of seek times n, we will see the total number of concurrency constitutes, which will be a lot more expensive. Okay? What we will do now, we will give a brief idea of what we did in our on-the-fly MHP analysis work. This work was done by Sonali Saha, and this was published in PPOP 22. This is the block diagram of the whole procedure. We first take the old AST, new AST, the new PST, and the old MHP map, and give it to the AST matcher that tells yes, is there a change or not. If there is a change, what type of change is it? Okay, the change type, it could be an addition or deletion, and the node which is being added or removed. And this PST is passed along here. Depending on whether I am adding or removing, and depending on the type of the node, we will call the appropriate corresponding functions. And this function will return an updated MHP. Okay? We will look at two simple procedures. Well, one of them is simple, one of them isn't. To give you an idea, let us start. Okay? We will start with add sequence statement. That is, I have a statement, I already have a statement N. I want to add a new statement L. Let's say before. Okay? How do I compute the MHP information of L without computing the MHP information of the whole program? Now, what I will do, I will take this N and I already have its MHP information. Let's call it as C. Okay, I'll compute it, and then I know, hey, this L will run in parallel with the same set C. Wow, I don't have to compute too much. So the MHP of L includes C and maybe something more. What can it be something more? If L is, say, inside a loop, and I may get back to L inside a task, then I have to add L as well. We'll skip that for the details. But more or less, based on the MHP information of L, I could compute the MHP information of L. And now I also have to add L to all these nodes in C. That is, L runs in parallel with M, and they run in parallel with L. Okay? What if you may ask, L has no predecessors? No problem. Then MHP of L is empty set. Let us now look at one more statement that we may add, which is a finish statement. This is slightly more involved. Okay? Here I have a PST. In this PST I have statements like S1, S2, S3, etc., which are simple statements. A1, A2, A3, A4 are asyncs, and F is the finish statement that I am adding. Say E is the nearest surrounding finish or async ancestor of F. Before adding F, I had a statement like A2, A4, which are asyncs. These may run in parallel with the statements that may come after F, right? For example, A2. Now that I'm adding F, A2, A4 may not run in parallel with, sorry, A3, A4 may not run in parallel with A2 anymore. Okay? So what I will do, I will think, aha, what other statements are there which are getting impacted because of this finish? Okay? There is one more statement whose MHP information sometimes may affect F, which is S1. Now you may wonder why. Why should I worry about S1 if it is impacting F? Maybe S1 and F are inside a loop. As a result, if A3 and A4 are starting here, after the end of the loop iteration, I may execute S1. So A3, A4 may run in parallel with S1 as well. But now that I add this F, A3, A4 will not run in parallel with S1 anymore. So I compute one such set which are getting affected because of this F, and which will not run in parallel with this A3 and A4 because of the addition of F. That set for us was S1, S2 and A2. So what I'll do, I will take away from the MHP information of every child of A3 and A4 this set M, and vice versa. Now you may say, aha, now that I have done this part fine, I have removed those that wouldn't run anymore in parallel with A3 and A4. Am I done? The answer is not quite. I have to do one more part. I have to incrementally add the e-asyncs for A3 and A4. Okay, so what did I do? First remove the MHP information and then added the required MHP information for A3 and A4 incrementally. Okay. In the paper, you can find detailed algorithms for adding and removal of every other construct, finish, async, atomic, if else, if loops, and so on. Okay. Talk about the complexity. For most of the statements, our complexity is order n, and compare that to the complexity of iMHP, which is order c times n for all statements, because it's doing whole program analysis, right? So if I have k updates, my gains are k times c, which can be pretty large, as you will see in the evaluation. We perform evaluation on two benchmark suites. One is IM suite. So this is an existing benchmark suite. We removed 20% of the nodes and added them one by one and treated them as updates. We also generated a host of synthetic kernels and had done both addition and removal. Okay? And we compared against the fastest competitor. Basically, for each invocation, for each update, I am invoking iMHP once. We show that on average, our gains are around 90% for both synthetic and IM suite kernels, which is huge, right? To conclude, we show that it's important to have on-the-fly MHP analysis for our task parallel languages. We provide algorithms to compute MHP analysis incrementally when the code may change, okay? And we show that the complexity improvements are pretty high, k times c for k updates. We have implemented this in Eclipse plugin, which is available if you want. And we show that our proposed algorithm leads to massive improvements. If any of you are interested in this and want to go for future work, please feel free to contact. We are very happy to see how we can extend it for interprocedural on-the-fly MHP analysis. With that, I will stop, and if you have any questions, I'll be very happy to take them. Thank you.